Hi everyone, welcome back to today's session. We are discussing on a case study that is building a multi-database backend, a fintech case study. Over here, I am building a backend that uses three different databases: Supabase, MongoDB, and Neo4j, all working together behind one fast API service. Moreover, I want to actually answer the most important question: why would anyone need three databases at once? I'll walk you through this project and show you how it exactly works, why I made each decision, and I'll show you by running live. By the end, you will understand not just what I built, but why, which is what actually matters. So let's get started. The first question is, why three databases? Why I decided three databases: Supabase, MongoDB, Neo4j. In a real fintech app, you've got three genuinely different needs. Three genuinely different needs. You need user accounts and logins. That's an authentication problem handled by Supabase. You have got transaction receipts. That's a flexible document. That's a flexible document. And this storage problem is handled by MongoDB over here. And you need trace relationships. That is your money tracing relationships between accounts. Who paid whom? Which is fundamentally a graph problem handled by Neo4j. So instead of forcing one database to awkwardly do everything, each one here is doing exactly what it's naturally best at. Let's move ahead. Here is the architecture diagram. If you understand this architecture diagram, you basically understand the entire project. Every request starts here. This could be Swagger docs, a curl command, or a front end. Doesn't matter what sends the request, it always lands in the same place: FastAPI. Inside FastAPI, I organize things into four groups of routes: handle login, manage transaction receipts, manage payment relationships, and the special one, handle an actual payment. Now here's the first fork in the road: auth routes, that is sign up and login, go directly to Supabase. But every other route, transactions, relationships, payments, first passes through this box labeled doorman. That is JWT verification. This one single function, that is get underscore current underscore user, reused everywhere, and its only job is look at the request. Yeah, and its only job is look at the request. Check for a valid login token. Valid login token. And ask Supabase, is this real and whose is it? If the answer is no, the request gets rejected right there. It never even reaches the MongoDB and Neo4j. If the answer is yes, the request is allowed to continue. Okay? First, it never reaches. If yes, then it is allowed to continue. Now, Let's focus here and here. Now see, Supabase has two arrows pointing in this diagram, this and this. One from auth for sign up and logging, and a separate one from the JWT verification for verifying tokens on every other request. Same database, two different jobs. Same database, two different jobs. Once a request clears the JWT verification, that is the doorman, it goes to exactly one database depending on what it's asking for. So if there is transaction routes, then it only talks to the MongoDB. See the error over here. Sorry, see the arrow over here. If relationship routes, then it only ever talk to Neo4j. Check this one. This arrow, I think it has got mixed up. Clean separation. It is a clean separation. Each route does one job against one database. And there is this one, this payments only box. Now this box has two arrows. One goes to MongoDB, if you see this, and the another one goes to Neo4j. Now this is deliberate and it's the actual centerpiece of the whole project. A single request here does two separate writes to two separate databases. And I'll show you exactly why that's useful and exactly how I made sure it is safe in a few minutes. For now, the one sentence summary of this entire diagram is auth is open. Auth is open. Everything else needs a verified login. And only one endpoint touches two databases at once. Two databases at once. Okay, let's continue with the next slide. So this one is on project structure. Let me go to the VS Code for it. Okay, right. Now over here, I have three folders. One is DB, another is models, and third is roots. Now this DB. Now this is where each database connection lives. One file per database. You have supabase.py, mongo.py, and neo4j.py. Another folder, models. This is where I define the shape of the data using Pydantic, such as what sign up request looks like, what a transaction receipt looks like. And the third is the roots folder. Roots folder. And this is where actual API endpoints live, organized by feature such as auth.py, transactions.py, relationships.py, payments.py. Now this pattern, connection file, then model file, then root file, repeats for every single database I added. Okay. Now let's come over here and check this Docker Compose YAML file. Now, if you see over here, MongoDB and Neo4j, they run locally through the Docker. This file spins up both. They just spins up MongoDB and the Neo4j. But Supabase is different. This Supabase is different. Why? Because it is managed cloud service. So there's nothing to run locally for that one. Just a URL and an API key and an API key. Now let's move towards next slide. That is Supabase authentication. Now we have sign up and login via Supabase auth API, returns a JWT access token, the doorman which I was talking about, and protects every route that touches money. Let's get to the Swagger docs over here and try to understand it from there. Let's get to the project. First, start Docker compose up. Okay, I think it's working. Let me recheck this again. Okay, container PyLink, Mongo up, PyLink, Neo4j up. Now, uh, then, hmm, okay, I think I missed something. The UVCon. Yeah, now I think it's working. Okay, now let's start with the authentication. See, this is the foundation everything else builds on. FastAPI auto-generates this interactive documentation page, which made testing everything throughout this whole project incredibly fast. And no need to build a front end just to try things out. So, first, signing up calls Supabase Auth API, real production grade JWT authentication without me building anything from scratch. So, if I go over here, let's try this out. Let's put in, okay, let's execute it. Now, logging in gives back me this access token. Okay, this access token. Now, think of it like a wristband at a concert. Once you have it, you don't need to show your ID again at every door. You just show the wristband. Okay, now let's get it authorized. Copy this, scroll up at the very top, click on authorized, paste it over here, and click authorize button. So every protected route in this API checks for that wristband. Okay, before letting the request through. Okay, now, okay, we are in. We are in over here and we have got this bearer token and this. Now let's see what else our next slide is all about. Transaction receipts. Okay. Documents, not rows, flexible schemas, no migration needs any fields. Okay. Now, in a relational database, think Postgres. In a relational database, think Postgres, which is actually what Supabase runs under the hood. Every table, every table has a fixed structure. Every row must have the exact same columns. If I want to add a new column, say 6 months from now, I can't just start writing with that new field in Postgres. I first have to run, suppose I want to add a new field. Okay. So I just have to run a migration script that goes and updates the structure for every existing row. On a big table, that can be slow and it's always little risky. And it's always little risky. Let's come over here. Let's go to models transactions.py over here. Okay, check over here. See, MongoDB in comparison to uh, Supabase, in comparison to Supabase, doesn't work that way. Okay, it stores documents, not rows, in a fixed table. This MongoDB stores documents, not rows in a fixed table. And each document in the same collection can have completely different shape. Now look at this metadata field. Okay, optional, dict, strne, none. It is typed as an open dictionary, meaning any JSON object, any keys, any values, or nothing at all. Okay, so transaction I save today might carry method is card in its metadata. A transaction I save 6 months from now, say it could be crypto, payments. Okay, now that carry different method such as crypto wallet address. Now both of those documents sit in the exact same MongoDB collection side by side with totally different shapes inside metadata. Okay, if no see I am comparing this with Supabase, a fixed structure database. But here MongoDB is flexible and I have made it flexible through this, and this provision is only possible in MongoDB. Now I never had to run a migration in this case or change any database structure to make this work. To make this work. Okay, are you getting my point? What I'm trying to say over here. But let me give you one honest caveat over here. Because this flexibility is also MongoDB's most common criticism. Without any discipline, a collection like this, a collection like this can turn into a messy, inconsistent documents over time. And that's exactly why I didn't make the entire receipt flexible. Only metadata is open-ended. Now fields like amount, currency, sender ID are still strictly typed and validated by Pydantic. and validated by Pydantic before anything gets saved. Before anything gets saved. See, before anything gets saved. So structure it where it actually matters. Flexibility where it genuinely helps, not flexibility everywhere by default. So I haven't just made this currency amount sender ID flexible. This was my main focus because later on the transactions could be with anything. It could be crypto, it could be net banking, okay, it could be card or anything. Okay. Okay. Let's me show you something. Let's get over here. Now post transactions. Right. Let me try this out. Suppose uh, sender ID is, let's take Adam. Receiver receiver ID is Jerry. Jerry. Amount is 50. Let yeah, let it be USD. And let's say note is dinner split. And method. Okay. Now let's go with the method over here. I'm going to take it as card. Let's execute it. Yeah. See, now every receipt over here gets a MongoDB generated ID. Gets a MongoDB generated ID and a server side timestamp. Server side timestamp. Okay. And never trusted from the client. Okay. Now, I think you've got this part, right? I hope you understood what I'm trying to say over here. See, I've used method as card over here. I have made this flexible. Okay. If I clear this and reset this, see, additional prop 1. I made this flexible and I've got this. Okay. Okay. Let's see what we have next. Now let's get to another topic that is Neo4j payment relationships. And this is the part which I'm very much excited about because it's the actual reason this project needed a third database in the first place. Okay, let me go back to this particular file and let me go to app roots relationships.py over here, and I want you to focus on this particular function and then this query. See, what I'm trying to do over here is that when someone sends money to someone, what things are important? Who sent it? Who received it? How much the money sent? And when it was sent. Now focus on these words, merge and create. Now merge, I use merge for the users, users, sender and receiver, but create for relationships. So here merge means find or create. Let me show that. Now here merge means find or create. Okay. Now, it means either find someone if you are able to get that person's name or create a new one. Okay. So what it does, it will never create a duplicate value. It will never create a duplicate value. Okay. Now create, it means make a new one. Always make a new one. Since every payment is its own distinct event, so just create a new one. Okay. Um, Let me show you one more query. If you scroll down and focus on this, get connections, focus on this query, or just focus on this particular line. Okay. This is important. This one is much more important. And this is worth it. Now, this single line, this single line means follow payment connections. 1, 2, 3 steps deep. 1, 2, 3 steps deep. This answers who has this person paid, directly or indirectly, in just one Cypher line. This is Cypher. You know, in Postgres, you write SQL commands. Here you write Cypher commands. Okay. Now, if you compare this with a relational database, this would mean this would mean multiple nested joins, multiple nested joins, and it gets messy fast as the chain grows. Okay, now let's prove it. Let me show this to you in Swagger over here. Okay, I'm going to build a chain over here. So let's go to post relationship send to. That is A sent to B, B sent to C. Okay, suppose the name is Charlie, sending it to Rohan, and he sends 100. Okay, let's execute this, and we have got 200, that is successful, with sender ID Charlie and receiver ID Rohan. Let's do one more payment from Charlie to Rohan, now from Rohan to someone else. So reset this, Rohan to Rohan to Kristen, Rohan to Kristen Bale, and the amount is 50. Let's execute this once again. Okay, Rohan, Kristen Bale, and 50. Now let's check the relationship connections over here. So from Rohan to Kristen, Kristen to this. Okay. Okay, let's first go to straight away to, then I'll compare this with that. Let's go straight away to Neo4j and let me show you something very interesting, what I'm looking for. Okay, this is Neo4j interface, the community edition, which is completely free and running locally in Docker. And this is going to give you genuinely the clearest way to explain the why graph database exists. Now let's run this one. Match user are sent to mm, let's organize this properly. Okay, let's do this. Now see this. Charlie to Rohan, Rohan to Kristen. Now let's come over here. I want to show you something very and much interesting over here. Charlie. Now let's compare. Charlie to Rohan, Rohan to Kristen Bale. Charlie to Rohan, Rohan to Kristen Bale. Okay. Now, if you see hop 1, that is Charlie paid Rohan directly. Hop 2, Charlie paid to Bale indirectly. Okay. And same goes with this one. Charlie paid to Rohan, Rohan paid to Kristen. This is the table form. Charlie sent to Rohan, Rohan sent to Bale. See, Charlie is sending to Rohan, and then Rohan is sending to Kristen. Okay, makes sense? This is what I wanted to show. This is what I wanted to show you. Okay, now let's get into the another interesting topic. Uh, this one, the payoff, one endpoint, two databases. One endpoint, two databases. But first, app routes transaction route pair. Okay, transaction route pair. Over here, now we see if I am checking it correctly. Yeah. Now, let me show you the problem first. So the fix actually makes sense. See this sender ID field over here. See this sender ID field. The person calling this API just types in who they claim the sender is. Let me explain to this. The person calling this API, just types in who they claim the sender is. Who they claim the sender is. And that's the issue. I could be logged in as myself, but still type in someone else's ID as the sender. And the system has no way to know that I'm lying. The system has no way to know that I am lying. So technically, I could create a transaction that says this other person sent this money even though they never did, even though they never did. And here's how I fix that. If you go to app, models, and payments.py and focus on this payment create. Now look at these fields: receiver ID, amount, currency, note, metadata. Okay, metadata. Now, what is missing over here? What's missing over here? There is no sender ID. There's no sender ID anywhere in this list. This is the actual shape of what the client is allowed to send. Since I never wrote sender ID into this model, there's generally nothing here to fake. The field doesn't exist to fill in, hide, or trick. So, where does the sender actually come from? The question is, where does the actual sender come from? Okay, he comes from he comes over here, from payments.py over here. He comes from over here, over here. That is sender ID is equal to current user ID. This doesn't come from the what the client types. If you click on this, it goes over here. If you click on this, it goes over here and it comes over here. See, it comes from here. It comes from the login token. Login token. The same token we checked back in the auth section. So instead of asking who does this person say they are, the code asks who did we already verify this person to be. When they logged in, only that answer gets used. Only that answer gets used. I hope you're getting it, what I'm trying to say over here. Okay. Okay. I hope you're getting it, what I'm trying to say over here. Now, let's go to uh, Swagger and let me show you post payments. Now, if you see the body over here has no sender ID field at all. The request body has no sender ID field to fill in. No sender ID field to fill in. Okay. Now, let's execute get transactions. This one. Let's execute get transactions and also let's check the connections. Now, first let's go to post payments, create a new payment option over here. Okay, suppose receiver ID. No, there is no sender ID over here, as you can see. Receiver ID, suppose it is Mega. Okay, Mega sends 200 US dollars and note is pay. Now note the sender ID in response. This will be your real logged in Supabase user ID. Okay, and this transaction ID. Let's verify in MongoDB. Let's verify it in MongoDB. Get transactions. Let me copy this thing first. Sender ID. Sender ID. get transactions. Okay, let me execute. Now, new entry in the list, new entry in this list. I've got a new entry in this list. So I've got Megha, amount 200, and the sender ID is the same exact matching ID. If you see last three, FE110EC, FE110EC. Make sense? It makes sense, isn't it? Now, let's verify this in Neo4j. Let's verify this in Neo4j. Let's go to relationships connection user ID, and over here I type this and execute and check this. Focus on only this. Source user ID, connections user ID, Mega Hopes 1. So name showing up here. One request, two databases, both correctly updated, both using real logged in user's identity. Okay. I hope you're getting it, what I'm trying to say over here. Okay. Okay. Uh, right. Okay. A few things I would like to show that I added over here to make this feel closer to real system. If you focus on this, every amount field across the entire project rejects zero negative values consistently. Everywhere money appears, not just in the main flow. So why? Because I have set the field to greater is equal to zero. That's why it won't give me zero or negative values. Okay. Now in the main.py, I have added global exception handler. So if something unexpected breaks, like a database briefly goes down, the client gets a clean, safe error message instead of a raw Python crash. Okay. Anything goes down, the client gets a clean, safe error message instead of a raw Python crash with internal details exposed over here. So this feature I have added over here. Okay. And I have also run a test full flow script. Okay. Now this runs the entire flow end to end automatically. Let me show you how. I've created a login over here. Okay. The login part over here. Okay. Then I have created a payment part over here. Payment part over here. Okay. Then I've also made it see payment created, sender ID, and then verify the receipt exists in MongoDB. MongoDB verification part is also done over here. Okay. Now let me show you. Let me run this file. Let me run this file. Python test underscore full flow dot py. See, login is successful. Login is successfully. Sender ID is this. Then create a payment. Writes to MongoDB plus Neo4j. Verify the receipt exists in MongoDB. Receipt found in MongoDB with correct data. Verify the relationship exists in Neo4j. If found in Neo4j connection. Full works. All checks passed. All checks passed. So login. Step one is login. Okay. And then create a payment. That is step two. Okay. And then verify it is step three. So this particular script is showing all the steps. Okay. All the steps. So this one command proves the whole system works instead of manually clicking through the docs every time. I was going to the Swagger and clicking a bunch of links over there and showing you how it works. Instead of that, I created one complete script, okay, where I have put everything and I have tested it and it is running successfully. And it is running successfully. So now, let's recap what we have learned today. Let's recap what we have learned today. Three databases, JWT secured, full code architecture diagram on GitHub. So this is the PayLink case study. Three databases, each doing what it's generally best at, tied together safely behind proper authentication and tested end to end. The full code, architecture diagram, and all the design decisions over here are on GitHub. Okay, you can click it, fork on it. If you find it useful, you can make changes if you want to, because this gives a clear view of using three databases all together and how to use them and for what purpose each of them are used. So I hope you have learned something new. If you like it, subscribe it. If you have any questions, please put in the comments sections or ping me. Okay. So thanks for watching. I'll see you in the next one. In the meantime, happy learning. See you soon.